Okay, welcome to chapter 15. I don't know how long this one's going to be. It looks like a long one because it's got like 2 pages. So we'll see how it goes. Number one, what is another way of writing x equals a to the y power? Now, of course, you can see the answers are all logs, right? So you can tell that this is based off a logarithm of the problem. So let's talk about back in the day, before I answer this question, back in the day, we did, I don't remember how the letters were written, but let's say it was a to the x power equals b or something. I don't remember exactly the way it was. Actually, no, I think it was b to the x equals a is what it was. Anyway, this is an exponential equation, and we are going to write this exponential equation in logarithm form. Now, this isn't a math problem. This isn't me solving this equation. This is just me transforming this in a different format. And to do that, this equation in a log format is a log with a base b of a equal to x. So how that works, give me 1 second, I'll be right back. All right, so how that works, essentially, again, you're not doing anything other than just rearranging some of the numbers. So this b value, whatever that number is, will become the base of the log. This exponent here, whatever that exponent is, will become what this logarithm equals. And the a value that the original thing equals is the kind of the key component of the main part of our logarithm. So for example, if I had, let's say I have 7 squared equals 49, this same exact equation can be written in log form as log with a base 7, because remember this main 7 here, that quote unquote the b value in this case, would become the base of my logarithm. So it's a little miniature 7 now. Of 49 equals 2. So keep in mind, and I'll circle this. I got colors here. I forget why I'm using pink. I used pink last time, but 7, right, is my b value. My b value becomes the base of my logarithm. 7 becomes the base of my logarithm. My exponent, x, becomes what it equals. So my exponent, which is 2, becomes what it equals. And then 49, which is my a value becomes the main part of my log. So the 49 that this equals becomes the main part of my log. So you can see how you're just shifting the numbers around, throwing a logarithm in it, and that's it. And then what I like to do and kind of remember in terms of how things are positioned, because it's really all that matters is the positioning of these things, is that the 7, whatever's first here, is technically written first here. If you're looking at this just from left to right, the 7 is the first thing there. The 7's the first thing there, of course, besides the log. And then the only thing that kind of rotates is the second and third term, right? The 2 is written second up here, and then the 49 is written last. Whereas when you switch it, the 49 is written second, and the 2 is written last. So those kind of switch positions in terms of what's left, center, and on the right. But that's just my little way of kind of memorizing where all these numbers go. That's all it is, though. It's just moving the numbers into a different place. So when you look at number 1 and you have x equals a to the y power, imagine this maybe just as a to the y power equal to x. Okay, maybe this is the easier because it looks more familiar. But this is no different than what I was just saying about b to the x power equals a, and how I wrote this in logarithm form just a second ago. So take this and write it in logarithm form. And what I mean by that is just take the components here, take these pieces, and rearrange them into a log form. If you can do that properly, you can get the right answer. It's not going to be the end of the world for you, okay? Number 2, what is the base of the function ln x? So this one, this is just something you need to know. So I just have to tell you the answer here. But remember how, let me go ahead and kind of give you a little bit of backstory though. Let's say I've got log of x, okay? Log x. Now, I'm going to ask, what's the base of that log? Because remember, the last time, there's supposed to be a little number down here, but I don't see a little number down there. Well, if there isn't one, then that base is known to be the base of 10. So typically, you see a logarithm, you have a little number down there for whatever reason, right? But if that number isn't there, and we just see the log x, or, then we assume that that number is 10. We know that that number is 10. It always is 10. So that's called the common log. So if you ever see, in the calculator, for example, if I type in, just hit the log button and then hit log 8, it's technically doing a log base 10 of 8. So it's when the calculator reads log 8, it's really doing the log with the base 10 of 8. Okay. Now the thing is, for the natural log, it's kind of similar. The natural log of x is a regular log of x, but it's not with a base of 10. The natural log is the same thing as a log with a base e of x. Because remember, e and natural log go together. E does not equal natural log, but e and natural log kind of go together. They're a family. Can't have one without the other, really. So the natural log of x is exactly the same thing as the log with a base e of x. We just write it this way because it's easier than writing it this way. But they're exactly the same thing. Natural log of x is the same thing as a log with a base of e. So that kind of answers the question number 2. The graphs of a function and its inverse are symmetrical with respect to which of the following lines? This is always going to be true, okay? Whether it's logarithms or anything else. But let's look at a graph so I can illustrate my point. Let me go to my y equals. Let me graph anything and then graph the inverse. So let's graph 2x. The inverse of 2x would be 1/2 x. So I'll put 1/2 x. So let's take a look at those real quick, okay? So that's what those look like, right? It's not going to be very easy to tell on this graph, but it's somewhat there. So remember that graph. You can come back and look at it again. I'm going to give you another example here. So let me clear that. Let me clear this one, and we'll do another one. Let's do another inverse. So ln of x, natural log x, and e to the x are inverse functions as well. So let's graph those two and see what they look like. So there you go. Those are those two. Okay. Now technically that blue part is supposed to continue all the way down, but it gets kind of cut off because of the calculator screen, how it tends to work. It doesn't fit it in there, but that blue part does technically go down all the way. So remember that. Okay. And let's go back to my main screen. Any inverse function, let's do a little sketch what we just had. Let me do black. So we had, remember, it was 1/2 x. 1/2 x was something like this. And then we had 2x. 2x was something like this. And then we did natural log. I'm doing this all for explaining purposes, by the way. I'm just trying to teach you something about inverses. I'm not trying to work at any problem out just right now. Then we had the natural log of x, which was this function. Wait, it was more like this, I think. And then we had e to the x power, which was something like this function. So these graphs are symmetrical, but where are they symmetrical? Where are they being split? Where is that mirror that would slice them down the middle? They're not being mirrored across the y-axis because, you know, this side of the y-axis is not the same as, or it doesn't mirror this side of the y-axis. They're not mirrored around that middle part. They're not mirrored across the x-axis either because what's on top here, it's not mirroring what's on the bottom there. They're mirrored more diagonally, right? They're mirrored more diagonally. So that is the line, this line right here, the diagonal line, is the line y equals x. And it's called the line y equals x because it's basically at 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, etc. Or even -1, -1, -2, -2, -3, -3, -4, -4, etc. Because whatever the x is, the y is as well. So 1, 1, right? The point 1, 1. 2, 2, the point 2, 2. 3, 3, the point 3, 3, etc. So that's why it's called y equals x, because x and y are literally the same thing. 1, 1, 2, 2, 3, 3, etc. That makes up that diagonal line. Every inverse function, no matter what it is, whether it's 2x and 1/2 x, those are inverse functions, or whether it's e to the x or natural log of x, these inverse functions. No matter what the inverse functions are, they always, always, always rotate around the diagonal line y equals x. So it doesn't matter what type of problem you're doing. Number 3, the question's asking, what's the inverse symmetrical around? It's always going to be the line y equals x. Every time. That's how inverses are designed. They always switch over y over x, okay? Or y equals x. All right, so number 4. Number 4 is based on a property that you should remember. Now, remember when we did regular logs, we did log of like 8 minus log of 2, and I said, hey, let's put these logs together. And when we did that, we didn't actually subtract. The subtraction here meant that we divided the numbers into my log. So the log of 8 minus log of 2 would be the log of 8 divided by 2. Log of 8 divided by 2 ends up being 4, of course, right? That property is absolutely no different if it's the natural log. So natural log of 8 minus the natural log of 2 would again just be the natural log of 8 divided by 2, which makes, of course, the natural log of 4. So a minus sign always means division. Okay, so that's kind of what 4 is talking about. If you have the natural log of C minus the natural log of D, well, guess what? That's going to be the natural log of dividing those things. So minus is always going to be dividing. If it was plus, it'd be multiply. So if it was C plus D like that, the natural log of C plus D, this would be natural log of C times D. So logs are weird in that way because when you add them, you actually just multiply the values. When you subtract them, you divide the values. So just keep those little things in mind. Number 5. So number 5, I'm going to work out one that's different than this problem, but you can follow the same steps. I'll make it very similar. So let me make an equation that's like 2, we'll call it 2 log 3 to the 4th power, or not 3 to the 4th power, but log base 3 of 4 minus, let's say, log base 3 of, 12, okay? So keep in mind, it's very similar to what we just did. We have 2 logs, they're both log base 3, and we're going to combine them to make a log base 3 as well. And because it's minus sign, it's going to be, we're going to divide. Actually, let me make this a log, let me make it log 2. This will make the division part easier. So, but I can't divide them yet because this 2 is out of place. Now, there's a property we talked about long ago that if we have a log with a base of something and then a to some power or whatever, this exponent would get moved to the front. And so it would be written as that number, that exponent in front of the log as normal. Now, that's what happened to this 2. This 2 has been moved to the front. So where it really belongs is back up there as an exponent. So what this problem should say is log base 3 of 4 to the 2nd power equals, I'm sorry, not equals, but minus log base 3 of 2. And now knowing that 4 to the 2nd power is actually the number 16. So that's a very important step. That 2 is out of place. You need to remember that 2, because the front of the log, originally came from the exponent spot, which made it 4 squared. 4 squared makes that number 16. So now that I know that, I can actually combine these a lot better. So I've got log base 3, so when I combine them, it'll be log base 3. And since it's minus, it means dividing these values. So 16 divided by 2, for example, would be 8. Or you can write 16 over 2, it would be 16 over 2, but 16 over 2 simplifies to 8. So this is not the same problem, by the way, that you have on your paper, but it works very similarly, right? Do what I did in number 5, and you should be all right. So what is the domain and range of the exponential function y equals 7 to the x power? So let's look at the graph of that. Let's go back to our y equals. Let's look at the graph of 7 to the x power. Right? Is that what it is? 7 to the x power. Okay. 7 to the x power graph. So remember, domain is how much of the x-axis is used. Now, we don't see the whole picture here. We only see a small part of it. If we zoom out, it's not really going to help us too much, but we can try, Yeah, that just makes it worse in my opinion, but, or at least harder to see, but let's see. If we, imagine I set my y value. Let me go back and zoom in real quick. I'm just trying to make this picture easy to see for explanation purposes. Let me change my window. Let me set my y max to something ridiculously big. So y max, let's set it up to like 1,000,000. Okay. All right, that still kind of works, I guess. But anyway, our goal, let me put it back to normal. I guess that didn't help as much as I thought it would. But our goal is to figure out domain and range. So figure out how much of the x values are used, how much of the y values are used. So domain is how far left and right it goes. So if you look at this graph, it's always going to continue going to the left. Let me draw a sketch so I can annotate this a little bit better. Actually, can I just sketch on the screen? Okay. It's always going to the left over here. It's always going to be going this direction. Now on the right side, it's going upwards, but it's always going to go outwards and upwards. It's definitely going upwards a lot faster, but it is slightly continuing further to the right. I don't know if I just said left before, but it's always going to slightly go to the right as well. And it's never going to stop. There's never going to be a barrier where it cuts off. It's always going to be slightly going more and more to the right. And because of that, it's always going to go left and it's always going to go right, which means it'll all use up eventually the entire x-axis. So the x-axis would be all real numbers since it's going to use up the entire x-axis, all real numbers on the x-axis. As far as the range goes, range is how far up and down. So if we look at how far up and down it goes, it only goes down to here. Like this is the lowest point. There's a barrier here. It's not ever going to exist anywhere below the x-axis, but it does go up forever. It just does not exist below the x-axis. So the range is from 0 upwards, from the x-axis upwards. So the range is only going to be bigger than 0. So you're going to pick the answer choice where the x values use up the entire range because the x values left and right. It all goes completely left, completely right. So all real numbers. Whereas the range is only going from 0 upwards because it's bottomed out at 0 and then of course goes up forever. So everywhere above 0. To kind of quickly explain that one. Number 7. You don't know too much about this, but I will just quickly explain it. Let me type this problem into my y equals. So let's clear this. Remember how to type a logarithm in like that? The log with a base 12. If you hit math and you go to the bottom of this page here, the math button page, you got log base. And you choose that, you can actually type in the log with a base of 12. And it's log base 12 of x in this problem. So let's graph it. And we're asked, which of these is an asymptote of the function? So an asymptote is an invisible barrier for our function. And in this case, our barrier is, it's kind of hard to tell. So let me hold on. I'm actually kind of curious, real quick. Hold on a second. Let me see if this works. Math, log base, say twice. Oh crap, that's not what I wanted. Math, log base, say 12. And let me pick a negative number. Let's say -5. Okay, yeah, okay. Let me just make sure. So this graph, let me annotate it for you a bit so you understand what's going on here. Now, this blue line is supposed to continue. It doesn't, so it's a very common thing that these calculators do. But imagine that blue line continues and it's there. So what's happening here is that this function is clearly hitting some sort of invisible wall right there. It's really tough to tell, but you can slightly see that over here, the function is slightly increasing further and further. It's going to the right, but as it's going to the right, it's getting a little higher every time. So it's always going to be going a little higher every time, but it's very obvious that it's hitting this invisible barrier here because it's getting to that y-axis and then it's never crossing that y-axis. So that barrier that we see is called an asymptote. An asymptote is that invisible wall, that invisible barrier that our function kind of collides with. It doesn't actually hit it, but it limits it. So, and in this case, that barrier is on the y-axis. So that's our answer. But that's what an asymptote is. An asymptote is an invisible barrier that sort of cuts off our function. So let me just show you real quick another example of an asymptote, just so you get a better idea. So the function 1 over x, if we graph this, you'll see that this actually has 2 asymptotes. This has 2 barriers. So let me just point them out real quick, just so you have a decent understanding of it. It has a barrier here on the y-axis because you can see on the left side, that this function is getting closer and closer to the axis, but it's blocked off, and it's blocked off here as well. There's this gap in the middle that both functions are kind of hitting. They never cross it. They just sort of interfere with it. And the same thing about the x-axis. The x-axis is another barrier here because you can tell that that blue line is getting closer to that axis, but then it starts going sideways. It never actually ends up crossing that barrier. Same thing on this side. It gets closer to it, but it never crosses it. So in this case, there's two asymptotes. There's two invisible walls, one here on the y-axis and one here on the x-axis. And that's exactly what an asymptote is. Okay? It's just a barrier, an invisible barrier. All right, number 8. Which of these describe the rate of change? So remember, rate of change is slope. So if we look at the graph of this, go to our y equals, and let's look at the graph of e to the x. So remember, e is second in the natural log, the number next to 4, e to the x power. We can graph this, and we can see what it looks like. So now we're looking about the, what do we ask for? The rate of change. So remember, rate of change is slope. So if I look at this, it looks very flat here, but it's very, very slightly increasing the whole time. Something like this. If I zoomed in, it's going to be slightly increasing. So as you read this from left to right, it's slightly increasing more, increasing more, increasing more, increasing more, increasing more, and then of course it's increasing a whole lot over here. So from left to right, it's always increasing, right? So when it's increasing, that means it's a positive slope. So we always have a positive slope here because from left to right, it's always going upwards. So that narrows it down. Now, the question is it moving away from 0 or is it approaching 0? Well, clearly it's kind of near 0 at the beginning, but then it's running away from 0 at the end. When I mean 0, I'm talking about this x-axis. Think of 0 as like ground level, right? It's on the ground, sort of, but then it's getting higher and higher above the ground, so it's moving away from that x-axis. So it's definitely a positive slope that's moving away from 0. Okay. So we talked about transformations before. I'm going to mention them again real quick in this video. I already mentioned them in a previous video, so hopefully you remember. But f of x plus k, f of x plus k. I'm going to write all the different transformations real fast. F of x, and then f of k times x, so k in parentheses or k outside parentheses, and then negative f of x versus f of negative x. So all of these over here are vertical transformations, whereas everything on this side is horizontal transformations. Now, anytime it's being added, a number, whether it's being added outside or inside, this is a shift. So, for example, this right here is a vertical shift, whereas this one's a horizontal shift, meaning this one vertical moves left or vertical moves up and down, horizontal moves left and right. The k value will stretch it. So this will be a vertical stretch, whereas this one would be a horizontal stretch. And the last one flips vertically and horizontally. So when I see our function in number 9, we have regular log base 7 of x, and then we convert it into negative 15 log base 7 of x. I'm noticing that we've got this negative 15, and that's doing two things. That's multiplying a negative in front of the function, which is what this is, a k value that's being multiplied to 15 in this case, multiplying a number to the front. But it's also got that negative as well. That negative is doing this. So it's not only stretching it, but it's flipping it as well. So I'm looking for, obviously I've got the stretch part down. Compression is sort of a stretch, but it's more like a shrink. That's not the case in this one. So vertical stretch, reflection across the x-axis or the y-axis. A vertical flip means it's moving from this way to this way, right? So that would be across the x-axis. So it would be a stretch that flips across the x-axis. All right, number 10. Number 10 is also kind of similar to this, so I'm going to leave all these up here. Let's look at the functions, though, we have the regular function is ln x, and then the new function is 5 units right and 10 units down. So 5 units right, that's very key. 5 units right is a horizontal shift. So that means the 5 is inside the parentheses. So we're going to have a natural log. We're going to have the 5 inside the parentheses. Now, if it's to the right, it's minus 5. So minus is right and left is plus. That's something you kind of just need to memorize. It's sort of backwards from how you would think it is, but that's the way it is. So when it says it's moving 5 units right, I know the 5 units is inside parentheses because going to the right is a horizontal shift, and that means that the 5 has to be added inside. Or it's not added, it's subtracted in this case because it's moving to the right instead of to the left. And when it says 10 units down is indicating a vertical shift. A vertical shift is putting that number on the outside, adding it to the outside. But since it's down, it's actually going to be subtracting it on the outside. So that is the case. Now, if you ever forget this on the actual test, a real easy thing to do is, of course, just go ahead and graph it. Go to your y equals. You can graph the original function, which is ln of x, and then you can graph the new functions and see which one moves it down 10 and right 5. So, for example, if you want to graph answer choice A, you can do ln, and you can do x minus 5, and then minus 10. And you can graph and look at both of these. So the original one's there in blue, the new one is there in red. It's kind of hard to tell, so maybe if you zoom out, this might be a little easier. But you can tell that it's moved down. If we annotate this here, the blue one to the red one, it's moved down, and it's also moved to the right. So it's been moved down 10, and it's been moved to the right 5. It's kind of hard to see because it's a little bit smaller, but it's moved down 10 units from here to here, and then it's moved right 5 units. You can sort of count the 5 units there if you squint a little bit. And that's exactly what the problem said to do. And so that's what makes A the answer choice. So you can still use the graph and compare the graph and see which one, does what the problem said it would. Or you can just, if you remember all the transformations that I wrote down, that'll work as well. Number 11, what is the solution? Okay. So to work this one out, this one's definitely a tougher problem. Okay, didn't mean to hit that, but we're good. I'm going to work out one that's similar. So I'm going to say, let's say minus 1/3 to the x power equals 90. Okay, I'll just show you the steps. So anytime that your variable is the exponent, so you see x, my variable, is up there. It's very important that we get this variable and we move it out of the exponent place. It has to be moved back onto our level playing field. It can't be hovering up there in the exponent. Now, the only way we can take an exponent and move it out of there is if we use logarithms. So if we put this and make both sides logarithms, 1/3 to the x power equals log 90. So I need to make this side a logarithm so that I can move this x to the front. But if I make this side a logarithm, I have to make the other side a logarithm. So we're making both sides logarithms. So now I can take this x and I can move it to the front of my log. I can have x in front, and now log of 1/3 equal to log 90. So now the x is on my level playing field. So now if I want to get the x by itself, all I need to do is cancel out the log 1/3. So all I got to do is divide the log 1/3 off of it. But of course, I got to do that to both sides. So that will cancel this out, leave me with just x on the left, and x will equal whatever the heck this number is. Log 90 divided by log 1/3, which is, again, just something you can type in the calculator. But that's the process. Anytime you see that exponent is your variable, the variable is hovering up there, you have to move it to the front, and the only way to do that is if you make both problems, both sides of this, a logarithm. Okay, now it's also important to point out in number 12, we have 15 to the x equals 90. It's important that no matter what I do to the left side, if I do the same thing to the right side, it's not going to make a difference. So if I make this log of 15 to the x and I make this log 90, that these are still going to be equal to each other because I put the same thing on the left as I did on the right. I can also do the natural log of 15 to the x equals natural log of 90, because whatever I did to the left, I also did to the right. So whether it's a regular log or a natural log, it means the same thing. And it doesn't even have to be a common log. It can be any kind of log. It can be a log with a base of 9, for example. It can be a log of base 9, 15x, equal to the log base 9 of 90. Because as long as these are the same that I do on both sides, then the problem's always going to be equal to each other. And in number 12, that's exactly what they do. Log 15x equals I put 90, but it's 905 in the problem. But Jenny wrote log 15x equals log 905, and that's perfectly fine because she has the same thing on both sides, just that log. Mike put natural log on both sides, and that's totally fine as well. And then Bob put log 15 on both sides. But again, he put it on both sides, so it's perfectly fine as well. So technically what they all did is perfectly legal. They can do any of those. Now, we typically would use just the regular log, but there's nothing stopping you from just doing anything, I guess. They're all technically right, because as long as it's the same on the left as it is the right, it's not going to make a difference. All right, number 13 is an equation, so let me work out an equation kind of similar. Let me make up one. So let's do 3, and I'll have, let's say, 2 to the x plus 1 power equal to, no, these are more? Yeah, let's say plus 13 equal to 8. Okay, obviously this equation is way different than yours, but it solves through the same series of steps. So we're trying to get the x by itself, but before we get to this x, we have all these other numbers here that we need to cancel out, starting with this 13 in my example. So I'm going to cancel this 13. There's no reason for it to be there. So we're going to have 3. It'll be 2 to the x plus 1 power equal to 8 minus 13, which ends up being negative 5, right? Okay, well, that's good. Now, again, before I can do anything to get this x by itself, I still have this 3 that's chilling I can get rid of. Since it's 3 times that, I can just divide both sides by 3, and I'll cancel that out. So I have 2 x plus 1 power equals negative 5/3. Now, of course, hopefully your problem doesn't have fractions like mine does, but it doesn't matter. But now I'm interested in getting this exponent out. So let me actually rewrite this from where I'm at. So again, you can always rewind the screen if you need to, but I've got 2x plus 1 equals negative 5/3, right? So now I need to move this out of the exponent place. I've got to get rid of everything else. I just need to move this out of the exponent for 2. So to do that, I need to make both sides logs. So log 2x plus 1 power equals log negative 5/3. So now I can move this to the front. So it'd be x plus 1 in front. I got then the log 2 equals the log of negative 5/3. And now I need to cancel my log. I've got x plus 1, but I can't do anything there until I divide out this log 2. So I would divide that. I'd have x plus 1 equals whatever number this is. I would just type this in the calculator and get a number for it. I'm not going to do that just to save time, but whatever number that is, right, I would then subtract 1, and I'd have x. So x is going to equal whatever that number was minus 1 in my example, and I have my solution. It's basically a lot of algebraic steps, but it's all algebraic steps that you should be relatively familiar with. Okay, so your problem, you'll have to subtract 25, then you'll have to divide by 7, then you'll have to make the logarithms, move the x minus 4 to the front, then you'll have to divide by the log 2 that you end up having, and ultimately end up adding 4 to both sides. So I just told you what to do step by step. It's repeating the process that I did there, but I'm not going to do it for you. I want you to at least try that out on your own, and hopefully you do okay. Number 14 is the last one, and it's it's not the last one. Oh my gosh, this is a long chapter. Okay, so I apologize for the video being kind of lengthy, but it is what it is. I want to make up a different example. I'm going to say E, and I'm going to say I have x plus 3 equal to 50. Okay, so just like before, I need to get this out of the exponent place, and I need to move it to the front. And the only way I can do that is with logarithms. But because this is E, I'm going to use not just the regular logarithm, I'm going to use the natural logarithm. So I'm going to put natural log on both sides. So doing that allows me to move that to the front. Have the x plus 3 up there, and then natural log e equals the natural log 50. Now the good thing is natural log and e immediately cancel out. They're inverses. They don't even exist anymore. They simply just disappear. So it's really just x plus 3 equals to the natural log of 50. And so when I subtract 3, I have a final answer. So x will equal the natural log of 50 minus 3. Now this is not going to be the natural log of 47. Okay, it's not that, because the 50 is with the natural log and the 3 is not. These are completely separate terms. So it's simply just the natural log of 50 and then minus 3. If you want to put the 50 in parentheses to help with that, you can, to make it look a little better, but that is the answer. All right, so your problem works through the same steps. All right, number 15. Okay, so number 15, if you were to graph this, right, I'll make up a different problem. I'll say I have 3, and then I'll say I have 7 to the x power minus 84 equals 112. So if I were to graph this, I have to make sure that everything is on one side. So I have all this stuff on the left and only the 112 on the right. So it only makes sense if I just move the 112 over there. And so to do that, I would subtract this 112. And so that ends up ultimately being 3 still, 7 to the x still, but I've got to combine these. So negative 84 minus 112, I don't know, whatever that is, would be the number that goes there. So be negative 196, I think. I could be wrong, but I think that's right. And then it would be equal to 0. So that's the function that would have to be graphed. So basically, it's just moving one term over to the other side. As long as you can handle that, you should be okay. That's what number 15 you have to do in number 15. All right, number 16, you don't have to do any math at all. Just remember the solution to a system like this. It is a system because you have more than one thing graphed. Now pay attention that there's, I'll try to sketch this for you. The graph that you have, I want to make sure you can see this. So you've got your x-axis, you got your y-axis. It's very obvious you see a curve that goes like this, right? But if you look really carefully, at 10, there's another line that goes like this. And you can kind of tell because if you look at the ends, you can see those arrows coming out at the ends. It's very hard because it blends in with the grid really well, but there is that line. So the solution is where these two lines, this curved one here, and the one that's going horizontally at 10, it's where they cross. As long as you can figure out where they cross, whatever x value they cross at. So if this is like, I don't know, you kind of have to look. Whatever x value it is they cross at, that's going to be your solution. All right. Number 18. I'll just quickly say, if I have a log of, I don't want to use the same thing that they did, but let's say I have the log base 7 of 13, and I have the log base 7 of x. Because these logs, I'm just going to explain this so you can answer number 18. I'm explaining how number 18 works. So because these are both log 7s, right, that log 7 is the same as this log 7, that must mean that whatever's here has to be the same thing as there. So that would mean that x would have to be 13, because if this is 13, this has to be 13 as well. It's the only way they're equal to each other. It's the only way that makes them the same. So that means that 13 has to be equal to x, that whatever is inside here has to be equal to whatever is inside there. So if that went over your head just a little bit, let me try one more time. Let's say I've got the log, and let's call it y of a. And let's say I have that equals to the log base y of f. Well, again, because both log y's are here, and they're the exact same thing, that must mean that a and f are the exact same thing. Okay? So based off of that and knowing that, I think you might be able to get number 18. But if you're still confused, don't be afraid to just hit me up or ask me in class, okay? You can message me on Remind or whatever you got to do. Number 19 is something we didn't really do much of because we have the benefit of our graphing calculators, but this is based off something called the change of base formula. So I'll explain again, and then I'll use this explanation to try and answer number 19. So let's say I have a logarithm that's like a log base 7 of 12, okay? And I'm trying to figure out what number this is. Now, we are fortunate enough with our graphing calculators. Let me pull this back up. We are fortunate enough that I have the log base function. If I hit math and I go down and hit log base, I can actually type in that exact polynomial, right? And I can get the answer pretty easily. However, not all calculators have that feature. Most calculators just have the regular log feature, right? Where you can't actually type in that little 7, that base number, which of course means you're going to get a different answer. It's not the same thing. So how do people with a regular calculator solve something like the log base 7 of 12? Well, they use something called the change of base formula. So the change of base formula basically rewrites this as the log of 12 over the log of 7. So what you're doing here is you're changing the base from 7 into a common log. You can pick any base you want, but most people pick a base of 10 because a base of 10 is a common log, and all calculators will have just common logs. So you're changing this from a base of 7 to a base of 10. You're making this a common log. But to do that, you basically take the log of this main part divided by the log of the base part. So in that problem, if I want to solve this in the calculator, but I couldn't type in that little number 7, I would just type this in instead, because I don't need that special feature to type this in, and I can get the same answer. So let's prove it. So let's clear this one because it's irrelevant. But if I type in the log, regular log, see, normal log of 12 divided by, hold on, I got to close my parentheses, very important. And I divide it by the regular log of 7. See, I'm not using the special log base feature that my calculator has. I'm just using the regular log button. But I'm doing this, and I can get the same exact result. So that's called the change of base formula. That's how people with just regular calculators, and not these fancy ones, can solve that problem, even though they can't type in the little base number. So, for example, if you wanted to solve log base 3 of 14, but you couldn't type it in like this because you can't type in that little base number, then you would just type log of 14 divided by log of 3. And that's just the regular logs, and that's how it would work. So that's what number 19 is asking. If you have log AC, how would you type it in using the change of base formula? What would be the same exact thing? You would have, what and what. So it's based off of this pretty much, okay? I hope I did at least enough there to sort of guide you through it. Hopefully you got the right answer. If you're still confused, just again ask me. I don't want to give you the answer. I just don't want to tell you the answer. I want to explain the reasoning and have you figure it out for yourself. So that's going to be it. I'll see you guys in chapter 16, which will be the last chapter for the regular class. Chapter 17 will be the last chapter for my honors class. I'll see you guys there. Bye.